forces. We're going to start putting free body diagrams and F equals ma and Newton's laws together. First one we already touched on last day, the gravitational force. Symbol, we traditionally use Fg. Equation, F equals mg. It's F equals ma Dillon in disguise, except g is 9.8. Negative, well, you know what? We're going to include, instead of including the direction as a negative 9.8, we're going to say the direction is towards the Earth. And we may find some questions that it's easier, Tara, to let that be positive. Here is your new force. This is something called the normal force. So gravity we looked at. The normal force. This is a third law reactive force. It's an action-reaction force. I just hate that action-reaction phrase because I always found that so confusing. You know what? I said Newton's third law was forces come in. Yeah, you know what? Really what we're saying here is, okay. Oh, there. Forces come in pairs. That's how I describe Newton's third law. And the normal force is a reactive force to something else applied to it. What is it? It's the force that prevents us from falling into the ground. It's the force that a surface applies when you apply a force back on the surface. All of you right now, take your non-writing hand and push down on the desk. Are you applying a force to the desk? Yes. Is your hand accelerating through the desk? That must mean the desk applied a force back to you. What force is that? The normal force, we call that. It's the force applied to by a surface. It's a relative force. It's a reactive force. AJ, it's only as big as it needs to be. All of you, push down on the desk again. Harder! Did your hand go through the desk yet? No. Did your hand lift off into the air like Superman? Nope. You know what? The normal force got bigger. It's as big as it needs to be because it's one of the forces come in pairs forces. This is a bit of a tricky one. Kids have a tough time wrapping their brain around this because they want to say, hey, how can my desk or how can the floor or how can the wall, if I push against the wall this way, how can a surface apply a force? So the normal force is the force that prevents us from falling into the ground. In fact, all of you sitting on the chair right now, gravity's pulling you down into the chair. The chair is applying a normal force back onto you, and all of you are used to that. In fact, when that normal force vanishes, that's what gives your stomach a rush. Any good amusement park ride worth its salt mucks around with the normal force. Because, Perry, they can't change gravity. They can't. What they can change is the normal force that you're so used to experiencing. They can make that bigger or smaller. McKenna, you'll pay money for it. We like it that much. Question, I ask. What does a scale measure? So hopefully I've convinced you, key idea, a scale measures the normal force. You see, there is no easy way to calculate the normal force. You're going to hear me say, hey, what is the normal force? I'm never going to give you an equation to find the normal force. I'm never going to give you an equation to solve the normal force. What we are going to be able to do, Sam, is draw a good free body diagram and using Newton's laws, figure out how big the normal force has to be. This brings us to the classic elevator question. A classic physics thought problem. A 72 kilogram man, you okay? Yeah. Looking for whatever? Uh-huh. A 72 kilogram man stands on a Newton scale in an elevator. So Tara, this scale doesn't measure kilograms, it measures newtons. A little easier. What does the scale read if the elevator is, and I'm going to give you a bunch of situations. In the first situation, we're accelerating upwards at 3.2 meters per second squared. You ready? Riley, this is a job for a free body diagram. Here's the person. Dylan, what are the forces acting on this person? Get the obvious one. Darn right. Dylan, is this person in free fall? No, they're in an elevator. Which way is this person accelerating according to this question, up or down? That must mean there's a winning force upwards for that to occur. We're going to give that a name. We're going to call that the normal force. The floor is pushing up. Now you'll notice in the question, Tara, I said, what does the scale read? You'll notice there's no scale in my free body diagram. Why? What does the scale measure? Normal force. I'm going to put normal force in my free body diagram. He's being pulled down by gravity. The ground in the elevator is pushing him up. Who's winning? I didn't have an elevator on there. Normal force. That's what. Ready? Who's winning? Normal force. You notice there's no elevator in my picture either. I'm going generic here. Normal force. Who's losing? So my equation is going to look like this. Winner minus loser equals MA, net force. What's this question asking me to find? It's asking me to find what the scale reads. No, it's not. What does a scale measure? This question's really asking me to find the normal force. How to get the normal force by itself? By the way, the reason we call it normal is a mathematics word for at a 90-degree angle to. When you push down at the ground always pushes straight back up at you. If you push down on the ground, you're not going to feel the ground pushing you off at an angle to the side. Not unless the ground itself is at an angle to the side. Okay. How do we get the normal force by itself? Darn right. Normal force is going to be MA plus mg plus, Mr. Duick. That's not a minus there, it's a plus, honest. There we go. 72, 3.2 plus 72 times 9.8. What do you get? 975, anybody else? 976? Is he right? 976 or 975, rounding off properly, is it? Let's see. We have a disagreement here. 72 times 3.2 plus 72 times 9.8. I'm getting 936. Yes? Units, it's a force. Newtons. Elijah, remember when I had you doing the deep knee bends on the scale? You saw the scale was moving up and down? We can go from newtons to kilograms by dividing this by 9.8. Can you take that 936 on your calculator, divide it by 9.8? What would the scale read if it was in kilograms? Anyone? 95 and a half? Would this guy be feeling heavier or lighter right now? Heavier. This is what you pay for on the elevator. The elevator is an elevator of a sort. When it accelerates you up, you feel heavier. Why? Because the ground, the seat that you're sitting on, the normal force, has to push up on you higher to compensate for gravity and the acceleration of the machine. And if you haven't figured it out yet, we love that feeling. We'll pay money for it, most of us. B. Accelerating upwards at 2.5 meters per second squared. This is a job for a free body diagram. What are the forces acting on this person? Get the obvious one. Gravity. Now I use Newton's laws. Is this person in free fall? Nope. In fact, it says they're accelerating upwards, which means there must be a winning force up. What? The ground, the scale, the normal force, the surface pushing back against him. In fact, I get the same equation as I had in the previous one. I get winner minus loser equals M8. Don't memorize the equation, though, because I can come up with a million variations of, you know what, memorize or understand how to do a good free body diagram, Newton's laws, and you can go winner minus loser and derive the equation. Normal force is going to be ma plus mg. It's going to be 72. This time the acceleration is 2.5 plus 72 times 9.8. What will this Newton scale measure? $885.6 newtons. If I divide by 9.8, right now he feels like he weighs 90.4 kilograms. He still feels heavier. He feels like he's being pressed into his feet. And remember, Riley, we said that our bodies are backwards accelerometers. He's not being pressed into his feet. If you feel like you're being pressed down, it's because you're actually being accelerated up. C. Yo.
So like if you did like squats on an elevator, would you like have a weight on? So
If you did squats on an elevator while it was accelerating up, now here's the key though, it's got to be accelerating up. Elevators don't accelerate up for very long, right? After about really half a second, they're at a constant speed. Understand the key difference. We're talking about acceleration, not speed. And this was also something, as a matter of fact, Elijah, that Albert Einstein thought about a great deal. He asked himself, what if I was in an elevator in outer space with no windows? Could I tell the difference between acceleration up at 9.8 meters per squared and Earth's gravity that I'm used to? And his argument was, I couldn't tell the difference. Maybe the reason I wouldn't be able to tell the difference is maybe they're the same thing. Maybe gravity isn't quite what I think it is. Maybe, and he started having some good thoughts from there. C, same elevator question. We're accelerating downwards at 5.2 meters per second squared. What would the scale read in kilograms? Okay, this is a job for a free body diagram. What are the forces acting on this elevator person? Get the obvious one, Zach. Darn right. Zach, is this person in free fall? They're in an elevator. Is this person in free fall? No. So there must be a force in the opposite direction. Is it bigger, smaller, or the same size as gravity? Which way is he accelerating? So who's winning? So I'll draw a normal force because he is standing on a surface, but I'll draw it considerably smaller. See that okay, Perry? Who's winning? Gravity minus, who's losing? Normal force equals ma. I think to get the normal force by itself here, I'm going to plus it to this side and minus that to that side at the same time. Is that okay, Sean? I'm going to get mg minus ma. That equals the normal force. It's going to be 72 times 9.8 minus 72 times 5.2 . 331.2 newtons. And just out of curiosity, how heavy would he feel right now in kilograms? Way lighter. Way lighter. This is what you feel when the elevator accelerates you downwards, and that is by far the most terrifying one for us. All of us are used to a normal force getting bigger. It happens every time you jump off of something and you land on the ground. For a split second, the ground has to push up on you harder because it's got to bring gravity and it's got to bring you to a stop. You're all used to feeling a normal force bigger. You're not used to feeling a normal force smaller. And that's why if you go on the elevator, you jerk when that normal force gets smaller. Now, you're still perfectly safe. By the way, there's no way he's leaving the ground. He's not floating in midair. He's still got plenty of downwards net acceleration and downwards net force. He's perfectly safe. But I'm telling you, how many of you get on the elevator? Right? When it goes down, especially the very first time you go on it, what? You feel like you're going to fly off the seat. You're not. There's probably still 3/4 of gravity acting on you. But just removing that 1/4, what the heck? Not used to that. So if you want to, Riley, you can also think the normal force is normally there. That's not why it's called the normal force, but I always think the normal force is normally there. Muck around with it, you've got a good ride. Try D on your own. I'll do it up here. Let's see if we get the same thing. Try doing it from scratch. Don't just, I'm going to copy out the previous. Try not looking at the previous one. See if you can derive it. Oop, that's wrong, Mr. Duke. See if you get what I got. I could be wrong. I typed that in a hurry. I think I'm right. Sam, am I right? Or no? Yeah. Okay. How many of you have ever been on a really fast express elevator? So I've been on a couple, and I have to admit, the nerd within me, if it's a fast express elevator where you can really feel the acceleration, and if it's not during rush hour so I won't tick off a whole bunch of people, gotta be honest, I'm taking it to the top floor, I'm getting in a crouch, I'm hitting go down to the main floor, and I have to see if I can jump just as it starts to go down to see if I can get a little higher than I normally do. You have to time it just right, and those express elevators have such a small acceleration, even for those, that it's not that much. Now, I will say, okay, full disclosure, I was staying for a couple of weeks in the dorms at the University of Alberta, and they had good, fast express elevators. And you can certainly feel the acceleration going up or down when you press the emergency stop button that you're not supposed to press and brake the elevator. 20 years ago, they can't prosecute me anymore. E. Moving downwards at a constant velocity. You know what? I have a feeling that this is going to be an important phrase. Of 3.2 meters per second. In fact, this is also going to go partly to Elijah's question about hypothetically could I increase the force or have lifting weights by. Here's my person. What are the forces acting on him? Get the obvious one. Gravity. Are they in free fall? Don't think so. Now, there is a normal force up. Because we're moving downwards, I think I'm going to say gravity is the winner, so I'll draw it shorter. I think my equation is going to look like this. Oh, winner minus loser equals MA. But here's the key. If I'm at a constant velocity, what's the acceleration? So really I have this. In fact, Matt, what I really have is this. You know what this means? Right now, gravity and the normal force are the same on you. You know how I know? Because you're not sinking into the ground like quicksand. You're not floating into the air like Superman. It means, Elijah, if you're in an elevator with no windows at a constant speed, you can't tell whether you're moving or standing still. Not in terms of your built-in internal accelerometer. You can try and listen for it, but if it's a really good elevator, you can't tell at all. You can only tell when the speed is changing. The normal force here would be 72 times 9.8, which is what? 705.6?
Yeah.
All right. The cable snaps. Ah! And the elevator begins to accelerate downwards at 9.8 meters per second squared in free fall. By the way, in real life, elevators have so many safety features, so many backup and redundant safety systems that it ain't going to happen. But supposing it did, what would the normal force be now? Jordan, you know what this is a job for? You know what this is a job for? A thing. Yeah, we're going to use the thing to get the thing, and if we're right, the thing will match the thing, and then you'll get the thing. Let's how about a few more nouns and a few less pronouns? Hey, there we go. Jordan, this is you in the elevator. What are the forces acting on you? Get the obvious one. Darn right. Are you standing on the scale? Are you standing on the scale in the elevator? So, who's winning? Well, it's accelerating downwards. Who's winning? Oh, by the way, in this previous one, turns out it's a tie. If I was really fussy, I should have drawn both those arrows the same length. I wasn't quite sure, Tara, and I said, well, you know, it says downwards. I'll maybe guess that gravity is winning, but do you notice we ended up proving that it's a tie if the acceleration is 0. Both arrows should have been the same length, right? Let's go back to here. Who's winning? Really? Which way are we accelerating, Jordan? Which way are we accelerating, Jordan?
Down.
Which arrow is longer, Jordan? Who's winning? You with me now, mister? Gravity. Who's losing? Winner minus loser equals my net force MA. Let's get the Fn by itself. I think I'll plus that there and I'll minus that there. Yes? We're going to get this. Mg minus Ma equals Fn. What's M? 72. What's G? 9.8 minus. What's M? 72. According to this question, what's the acceleration? According to this question, what's the acceleration? What are we accelerating at? I don't see a negative anywhere. Don't be including negatives. We're getting away from that now. According to this question, what's the acceleration? Perry, without a calculator, what is 7? No, I'll go back to Jordan. Without a calculator, what is 72 times 9.8? Take away 72 times 9.8. What's the normal force that this person would feel? We call this apparent weightlessness. He would feel like he was floating. See, it's not true weightlessness because is gravity still acting on him? Did it show up in my equation? Yes. True weightlessness is if you go to the edge of the universe somewhere away from all planets so that there's no gravity acting on you. That's actual weight. That's true weightlessness. Apparent weightlessness is if you accelerate downwards at exactly the same speed as gravity. And we can do that all the time. NASA has this great plane called the Vomit Comet. That's its nickname. This is how they train the astronauts for weightlessness. What they do is they take the plane to a high altitude and they dive down with an acceleration of negative 9.8. And because you're in an enclosed room, you can't feel any breeze on your face. All you know is suddenly the normal force has gone down to 0. You're floating. And you get about 26 or 27 seconds of apparent weightlessness. And then you got to pay the price because then they start pulling up. You get pressed down against the ground. They pull up. You really get pressed down against the ground because now the plane has to accelerate back upwards, which means the normal force is bigger. But when you get to the top, you get apparent weightlessness again. The normal force. New force number 2. Force number 2, air resistance. Air resistance is the force of air molecules bumping into an object that's moving through the air. Force of air resistance has a direction opposite to motion. It says, example 4, draw force diagrams for each of the following. So we're talking about a ball being thrown. In situation A, we're talking about this part right here, Dylan. In situation B, we're talking about on the way up. And in situation C, we're talking about on the way down. Got it? Situation A, this part. What are the forces acting on the ball? Get the obvious one. Darn right. When I do this, watch. Which way was the ball accelerating? Up. Has to be, because it has to be accelerating up, because if it wasn't, I can do this, it's not accelerating up right now. And when I let go, it's not going to go anywhere. I've got to be going faster than -9 I've got to take care of that so that when I let go, it keeps going. Yes? That must mean there's a winning force up. Draw it longer. Which force? My hand. How about force of hand? Situation B. This portion. Ready? Look, 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 look. Here, there. From when it leaves my hand to when it gets to the top. Let's pick right in the middle. Freeze frame. What are the forces acting on it? Get the obvious one. Darn right. And we also have air resistance. And air resistance always acts in the opposite direction of motion. So it would be downwards if we took air resistance into account. Situation C, on the way down now. What are the forces acting on this ball? Get the obvious one. Darn right. Which way is the ball traveling? Downwards. Which way is air resistance then? Upwards. Now, for a ball, air resistance is pretty small. Ball is reasonably aerodynamic. Although, you can curve these things through the air, so there must be some air resistance. Parachute, way more air resistance. It does have to do, William, with the cross-sectional area. Yes, it is a squared function. An arrow, not much air resistance. Very thin cross-sectional area. In diagram B, right there, how the heck can the ball be rising if all of the forces on it are acting downwards? Because acceleration is not the same thing as velocity. This is one of the things I'm trying to keep drumming into your heads, because kids always want to say acceleration and velocity are the same thing. They're not. You can happily be having a velocity up and an acceleration down. All that means, Matt, is you're slowing down, which it is on the way up. So, good explanation, Andrew. Sorry? Yep. It's slowing down. Perfectly fine. Perfectly fine. If the falling ball in example 4C is speeding up, write a force equation. Do you guys have to turn the page or not? Or you use one page? Okay, so same diagram? Okay, what are the forces acting on this ball? Get the... Oh, we already did that. Who's winning? Who's losing? Air. You know what? Your equation would look like this. Example 7. I think I'm nearly done. Yes? Yes, I am. Good. A 90-kilogram parachutist free falls for a time. Have I mentioned lately I jumped out of an airplane? And then opens a parachute. His new downward acceleration after opening the parachute is now 1.5 meters per second squared. A says, compare the forces that act on the system. Really, Jordan, what they're saying is do a good free body diagram. Figure out who's winning, who's losing. B says, write a force equation, winner minus loser. And then C says, find some. Okay. Let's do A. Here's my parachutist. What are the forces acting on him? Get the obvious one. Is he in free fall at negative 9.8 according to this question? No. So there must be another force acting in the opposite direction. Is it bigger or smaller than gravity, and how can you tell?
Smaller.
Why smaller? So there's my picture. Shorter arrow. What force? Air resistance, darn right. Okay. B says, write a force equation. Okie dokie. Who's winning? Who's losing? C says, find the force of air resistance. Okay, how would I get the F air by itself? Yeah, we've seen this before. I'm going to do that, and I'm going to do the little swapperoo doodad, right? Is that okay, Matt? It's going to be air resistance is gravity, there we go, take away whatever left is accelerating. What was the mass? 90 times 9.8 minus 90 times 1.5. What's the force of air resistance? Okay. Now, air resistance, we don't look at very much because it's a very, very complicated force. It changes all of the time. As you speed up, air resistance gets bigger. As you slow down, air resistance gets smaller. And this skydiver is speeding up, which means a millionth of a second after we calculated this, our answers are already wrong because air resistance just got a bit bigger. Oh, and when air resistance gets a little bit bigger, when this number gets a bit bigger, the overall acceleration gets a little bit smaller. Right? Eventually, you're going to find, Zach, an equilibrium point. Eventually, you want the acceleration to be 0, which means air resistance exactly cancels out gravity. And a parachute is designed so that that happens at a fairly slow survivable velocity. So you drift down at a constant speed, a survivable speed. There's your parachute. The guy who invented it, he invented it, I think, back in the 1920s, and he tried to sell the military on it, and they weren't interested. And so to prove that it worked, he drove to Washington. He called a press conference. His parachute was basically a giant umbrella that he wore around his waist like a skirt that would open up. He stood on the Washington Monument, and he jumped off and survived. Suddenly, the Air Force became very interested. Oh, it works. But there's a gutsy, I have confidence in my invention. I'm leaping off of a tall building. So, turn the page, or next page over. Yeah, it is turn the page now, right? Force of air resistance is actually not a constant value. It gets larger as speed increases. Eventually, a falling object will reach the point where the air resistance equals the weight, mg. We call this terminal velocity. And I can change terminal velocity because it has to do, Zach, with how much cross-sectional surface area is exposed to the air. If I want a smaller terminal velocity, I can tuck in. If I want a larger terminal velocity, if I want a larger terminal velocity, I tuck in. If I want a smaller terminal velocity, I lay flat, spread eagle. If I want an even smaller one, I got to get a bigger surface area, a parachute. Example 8, last one. Parachutist jumps out of a plane and free falls. They reach terminal speed. They maintain that speed for a while. They then open their parachute. They quickly reach a different terminal speed, and then they descend to the ground. Sketch a velocity time graph. Okay. By the way, I said speed, not velocity, because technically everything should be negative, but I don't want to draw something below the x-axis, so we're just going to look at speed. Here's our graph. Velocity, time. And specifically, we're going to talk about vertical speed only, because I know in the airplane he's traveling horizontally. Let's ignore that. So we start out in the plane, up there. What's my vertical speed while I'm still in the plane? Meant to be really obvious. 0. So there would be some amount of time where the graph would do that. Right? I jump. Woohoo! What happens to my vertical speed then? Now, as I get faster, air resistance gets bigger, the acceleration gets smaller. Really what I should be drawing is something kind of like this, because eventually I'm going to level off at a constant speed. Here is free fall. I've hit terminal velocity right there. I accelerate at my maximum right away, Riley, but the faster I go, the more air resistance gets, the smaller my acceleration until eventually I reach equilibrium. I free fall for a short while, and then what do I do? What's that going to do to my velocity? Okay. Boom! Get it much smaller, and I reach a new equilibrium, maybe right here. Now, in real life, this part of the graph, Riley, should be about 5 minutes of time long. It really should extend off the page, because I free fall for about 30 seconds. It should be 30 seconds. It takes a while to float down. We're not going to worry about scale because I don't want to go shooting off my page. Eventually, I come down to the ground, and I hit the ground, and now I'm at a velocity of 0. The stretchiness is wrong, but the shape is correct. That's what it looked like when I jumped out of an airplane if you asked me to draw the velocity time graph. Sketch the velocity time graph. Sorry. The speed time graph, because if it was velocity, this would all be below the x-axis because it would all be negative, right? So, what's your homework? Number 1, 2, 3, 4, 5 is good. 7 is good. Skip 8. There is no 6. I nuked it. 9 is good.